Under Pressure, Part 2, Just the Facts, is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. This video, Under Pressure Part 2, discusses atmospheric pressure, barometric pressure, gauge pressure, absolute pressure, and vacuum pressure. Pressure is one of the most common variables in chemical processes, and understanding how to use it is fundamental to chemical and thermal processing. Part 1 discussed what pressure or force per unit area is, how to use it, and some of the methods for measuring it. Three very common terms used when specifying pressure are absolute pressure, atmospheric pressure, and gauge pressure. If you had a differential pressure gauge with the pressure to measure on one side and a perfect vacuum on the other side, the difference in pressure between those two would be the absolute pressure. In other words, the absolute pressure is the pressure relative to a perfect vacuum. The unit when given in pounds per square inch is indicated as PSIA, A for absolute. For other pressure units, you would just have to put the word absolute after the unit. If you had a differential pressure gauge with the local atmosphere on one side and a perfect vacuum on the other side, the difference in pressure between those two would be the atmospheric pressure. In other words, the atmospheric pressure is the pressure of the atmosphere relative to a perfect vacuum. It is sometimes called the ambient pressure. As a variable or parameter, it is usually indicated by the subscript ATM or AMB or not. If you had a differential pressure gauge with the pressure to measure on one side and the local atmosphere on the other side, the difference in pressure between those two would be the gauge pressure. In other words, the gauge pressure is the pressure relative to the local atmosphere. The unit when given in pounds per square inch is indicated as PSIG, G for gauge. In other pressure units, you would just have to put the word gauge after the unit. The relationship among the three is that the absolute pressure is the sum of the gauge and atmospheric pressure. Conversely, the gauge pressure is the difference between the absolute pressure and the atmospheric pressure. For example, if you measure the pressure in a tire, you are measuring the pressure relative to the local atmospheric pressure, so it's the gauge pressure. If you need the absolute pressure in the tire, say for use in the ideal gas law, you can't just assume that the atmospheric pressure is 1 atmosphere, because the local atmospheric pressure varies with altitude and meteorological highs and lows. So to get the absolute pressure in the tire, you need one of three things. 1. An absolute tire pressure gauge. 2. An atmospheric pressure gauge. Or 3. A current weather report and your altitude above sea level. Absolute pressure gauges are easy to find, as a quick web search will show. Absolute tire pressure gauges are nearly impossible to find, as a quick web search will show. The local atmospheric pressure is easy if you have a relatively decent cell phone and you will get an air pressure app. The weather report will give you the barometric pressure, but except for airports, it won't give you the local altitude. However, a decent cell phone and a GPS app will give you your local altitude. We need to explain the concept of barometric pressure. It would be really nice if you could simply look at a weather website or on a weather app on your phone and get your local atmospheric pressure. But unless you live at sea level, the weather apps don't give you the local atmospheric pressure. What they do give you is barometric pressure. The barometric pressure is the local atmospheric pressure adjusted for altitude back at sea level. In other words, if you drilled the hole from your current location down to sea level and measured the atmospheric pressure at the bottom of the hole, you would get the barometric pressure. Conversely, if you start with the barometric pressure and correct it for your altitude, you will get your local atmospheric pressure. The formula to correct for altitude comes from the standard atmospheric model. However, these days most cell phones have a pressure sensor, and you can download an app that will give you the local atmospheric pressure. Continuing with correcting the barometric pressure, if you are in the troposphere, below 11 kilometers in altitude, Mount Everest is 8.85 kilometers, you can use this formula either for your measured local atmospheric pressure and altitude to determine what the barometric pressure is, or from the barometric pressure and your altitude to calculate what your local atmospheric pressure is. Note that air is very compressible, so the pressure doesn't vary linearly with altitude like it would for an incompressible fluid. The formula for air in the troposphere is that the barometric pressure is equal to the local pressure times 1 minus 2.25577 times 10. To the minus 5th h, where h is height or altitude above sea level in meters. That expression is raised to the 5.2558 power. The inverse expression is that the local pressure is the barometric pressure times the previous expression, but now raised to the negative of the previous exponent, or to the negative 5.25588th power. Notice that the local and the barometric pressure only have to be in the same units. They don't have to be in a nice SI unit, so feel free to use pounds per acre or furlongs of methanol if it makes the problem easier. Let's do an example. Let's say you go and measure the tire pressure in your bicycle tire, assuming you have a bicycle and you're currently in Claremont, California. Anyway, the barometric pressure, as reported by the local weather station, is 29.89 inches of mercury in Claremont. Your current altitude in Claremont is 1,340 feet, or 408.4 meters above sea level. So, what's the absolute pressure in your tire in PSIA and bar? Again, the A in PSIA means absolute. Well, let's start with the local and barometric pressure relationship. The local atmospheric pressure is the barometric pressure times the expression given, and we know that the barometric pressure is 29.89 inches of mercury. We'll convert the barometric pressure to the local atmospheric pressure at 1,340 feet. Then, we can plug in and calculate. That gives us the local atmospheric pressure is actually 28.47 inches of mercury. Because we're above sea level, you'd expect the local pressure to be lower than the barometric pressure. We'll convert inches to millimeters to get 723.2 torr, or 13.98 psia, which to 3 places is 14.0 psia. The gauge pressure is 36.0 psig, and the atmospheric pressure for all practical purposes is 14.0 psia. The absolute pressure is equal to the gauge pressure plus the atmospheric pressure. Adding those together, we get 50.0 psia, or 3.45 bar. Here's a spreadsheet of the solution to the problem. The first column is dealing with the standard atmospheric model and getting the various coefficients that we used in our local to barometric expression. The second column is the calculation of the actual problem. If you're curious about the standard atmospheric model, you can look up most of the information on Wikipedia or on various other websites. The interesting factors here are the lapse rate, which is how average air temperature varies in the troposphere with height. You drop by 0.065 Kelvin for every meter you go up. So if you increase your altitude by 1 kilometer, you will drop by 6.5 Kelvin. G is the standard gravitational acceleration. Next is the molecular weight of air in kilograms per mole, about 0.02896, or about 29 grams per mole. The value of the gas constant is interesting because it differs from the one that you'll find on the NIST website by not a terribly significant amount. This value is the one that is used in the US standard atmosphere. It is unclear why they use this one instead of switching to the current value. T0 is the assumed temperature at sea level, which is 288.15 Kelvin, or 15 degrees Celsius. The DOFPro high-power rocketry website goes into greater detail about the barometric altimeters, T0 and the lapse rate. Okay, then finally plugging in, you get the constants in the barometric to local pressure expression. The second column is the solution to the actual problem. We have our 1,340 feet, or 408 meters, altitude in Claremont, the barometric pressure of 29.89 inches of mercury, and the local pressure calculated from the barometric pressure, and the altitude as 28.47 inches of mercury, or 13.98 psia, which is 14.0 psia, the 3 significant figures. We have the gauge pressure of 36.0 psig, and finally, the tire pressure is the sum of the gauge and local pressures, 50.0 psia, or 3.446 bar. The spreadsheet is available on the website with some additional calculations on how atmospheric pressure changes with altitude. Pressure and pressure calculations are used extensively in chemical and thermal processes. A few final words about vacuum pressure and high vacuum. Processing equipment sometimes needs to operate at pressures below atmospheric. In PSI, it's indicated by PSIV, with V for vacuum. The vacuum pressure, or simply vacuum, is the difference between the atmospheric or ambient pressure and the pressure inside the process, reported as a positive number. For example, a distillation column with an internal pressure of 10 psia on a day with an ambient pressure of 14.7 psia would be described as having a vacuum pressure of 4.7 psiv, or having a vacuum of 4.7 psiv. The background image here is a vacuum distillation process. Advanced materials processing often takes place at pressures near zero in chambers such as the background image. In such cases, the pressure in a vacuum chamber is defined as high vacuum, HV, ultra-high vacuum, UHV, or extremely high vacuum, and given as an absolute pressure. The usual ranges for these three are HV is between 10 to the negative first and 10 to the negative 5th Pascal, UHV is 10 to the negative 5th and 10 to the negative 10th Pascal, and EHV is 10 to the negative 10th Pascal and below. The takeaways from this video are 1. Absolute, gauge, and atmospheric pressure are related by P absolute equals PG plus P ATM. 2. Barometric and atmospheric pressure are related through the standard atmospheric model. 3. The vacuum pressure is the absolute value of the gauge pressure below atmospheric. 4. The high vacuum, HV range, is from 10 to the negative 1st to 10 to the negative 5th Pascal. Ultra-high vacuum, UHV, is from 10 to the negative 5th to 10 to the negative 10th Pascal. And extremely high vacuum, EHV, is 10 to the negative 10th Pascal and below. Thanks for watching. This video is brought to you by the DOFPro team.